Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Mind Maps, we'll be dealing with the ninth chapter in the grade 12 syllabus for physics in CBSE. The name of this chapter is Ray Optics, which is expanded to Ray Optics and Optical Instruments. So in this chapter, we'll be using the help of this mind map in order to explain it. Mind maps are really easy tools in order to be used as last minute preparation tools. However, they can be pretty expensive, like this one. So they can be pretty extensive. So therefore, this video is devoted to explaining this mind map in some detail. So ray optics. Now in ray optics, what we're doing is we're considering light as traveling in a straight line. But if you remember our previous chapter, EM waves, we know that energy from the sun is transmitted in the form of electromagnetic waves, and light is a part of this spectrum. Now, how can we consider ray optics to be an accurate representation of light? Well, the solution is that light is a wave, but its wavelength is really small, about 10 raised to minus 9. So it's measured in nanometers, the wavelength. So therefore, in terms of real life applications, we can consider light as a ray in terms of large objects blocking its path, or whether reflection or refraction, etc. In the next chapter, that's wave optics, we'll be looking at some other features of light coming at the minute level. So right now, we're going to be considering that light is a straight line. It travels in a straight line. So in this chapter, we'll be looking at reflection of light. We'll brush up the topics of grade 10. Then we'll be looking at spherical mirrors and the sign convention for them. Then we will be diving into refraction of light. So in this term, we'll be looking at refraction through a glass slab, total internal reflection and critical angle, refraction on a spherical surface. Then we have the lens maker's formula and the lens formula. Then we'll be looking at power of a lens. After that, we'll be looking at refraction through a prism. Then we'll be looking at phenomena such as scattering of light. And finally, we'll be looking at the second part of this chapter, optical instruments. Here we'll be looking at microscopes, compound microscopes, and finally, telescopes. So let's jump right in to reflection of light. So in order to brush up our topics, reflection of light basically means when a ray of light travels from one medium to another medium and it bounces off to the first medium. So from this, at this point, it's trying to get into the other medium, but it gets sent back to the first medium. This is known as reflection. In reflection, we always have a change in angle. The change in angle may be 0 degrees or it may be very large. Now, reflection has two laws, and these two laws are mentioned here. The first law states that the angle of incidence is always equal to the angle of reflection. This is true even when the surface is smooth or even when the surface is rough. In this case, if light is incident like that, then this is the angle of incidence, and so this will become the angle of reflection. So it is dependent on the normal on which this reflection occurs. That's why we kind of feel as if the laws are getting broken in a diffuse surface or a rough surface, but in reality, it's just a normal that's changing. The second rule is that the incident ray, the reflected ray, and the normal to the reflecting surface are coplanar. So all of these rays, the normal, the incident ray, the reflected ray, all of this are part of one plane. So all of this happen in a two-dimensional structure. As you can see, this is what happens in a plane mirror where everything is smooth, and this is what happens in a spherical mirror where as we move along the mirror, we get differing reflected light rays. And this is due to the fact that the normal is getting changed as we move along. The same reason why in rough surfaces, we don't usually see uniform reflection. These are the two laws, and that is what we should be brushing up with respect to reflection of light. In a plane mirror, these rules are seen clearly. A plane mirror is basically a mirror with focal length at infinity, and the size of the image will be the same as the size of the object, and the image will be behind the object, so that means it's virtual and it's erect. It's also laterally inverted, so if you raise your right hand up, the image in the mirror will show its left hand up according to our view. Now let's look towards spherical mirrors. A spherical mirror is basically a mirror with a spherical reflecting surface. So if you take a sphere and then cut off, say, one portion of the sphere, then this part is what we refer to as the spherical mirror. Now, you can form two types of mirrors with a spherical surface. If the outer portion of the spherical surface is silvered, is coated with silver, then the inside acts like a mirror, and that mirror is called a concave mirror. On the other hand, if we're silvering the inside of a spherical surface, then the outer surface acts as a reflecting surface. This mirror is called a convex mirror. Both concave mirror and convex mirrors form images, and they are the two types of spherical mirrors. In a spherical mirror, we usually have the center of curvature. That means if we were to draw the entire sphere which contained this mirror, then the center would represent the actual center of that sphere. That's why this is called the center of curvature. The distance between the pole, which is the middle point of the mirror, and the center of curvature is called the radius of curvature. And the axis, which is passing through the pole and the center of curvature, which is horizontal, this is called the principal axis. Now, if you have an object placed somewhere and you need to find its distance with respect to the mirror, you measure it with respect to the pole, and this is called the object distance, or U. If you have an image and you find out its the distance between the pole and the image, you call that the image distance. Now, if we're to project parallel rays of light to a concave mirror, then all of these, they come together, they meet each other at a specific point on the principal axis. This specific point will be present in between the pole and the center of curvature along the principal axis. This point is called the focus of a mirror. It's basically the point where the parallel rays are concentrated, they are reflected to form a concentrated image. Now, in this year, what we're going to be studying is how to find out the focal length of a mirror, the radius of curvature of a mirror, the object distance U, the image distance V, and we'll also be learning about magnification. So in order to measure all these quantities, we need to follow some sign conventions. So the sign convention that we'll be using in this chapter is called the new Cartesian sign convention. In this, we take the pole as the origin. So this is similar to a Cartesian plane, except that the pole now becomes the origin. The principal axis here acts as the x-axis, and anything perpendicular to that is the y-axis. So if we draw an axis like this across the pole, then that becomes the y-axis. All distances in this plane, in this sign convention, are measured from the pole. So if you want to find out the distance of the object, you measure it from the pole. And over here, the sign convention also states that the incident ray is always from left to right. The incident ray always travels from left to right, whether it be a concave or a convex mirror. So therefore, we can also say that all distances measured in the direction of incident ray are taken as positive, and all distances measured in the direction opposite to the incident ray are taken as negative. So if we have an object here and we need to find its distance, you're essentially going opposite to the direction of the incident ray. So therefore, this distance is negative. If the image was to the right of the mirror, then you have to measure to the right side, which is in the direction of incident ray. So therefore, that distance will become positive. And another point is that the height of an object in the upward direction, perpendicular to the x-axis, is positive, while if it's perpendicular but it's pointed downward, then it becomes negative. So these are the simple sign conventions that we use in order to calculate quantities. So after deriving some equations, we arrive at the final equation called the mirror formula. This is the mirror formula. So in here, basically it states that the reciprocal of focal length is equal to the sum of the reciprocals of image distance and object distance. So basically 1 by f is equal to 1 by v plus 1 by u. The values for v and u change in accordance with each question. And lateral magnification for a concave or convex mirror will be measured as h2 divided by h1. h2 is the height of the image and h1 is the height of the object, which can also be written in terms of distances as minus v by u. Again, v and u's signs may change with respect to each case. In grade 10, you have studied about the different cases of concave mirror images and convex mirror images. So in this mind map, there is no mention about it. But then if you really do want to know about it, then go back to our episode called Light Reflection and Refraction in grade 10, where we'll be discussing about all of these stuff. So within a short span of time, we've covered everything that is reflection. Reflection is a short topic in grade 12. The bulk of ray optics is actually based on another topic, the other topic that we studied, which is refraction of light. So what exactly do you mean by refraction of light? Refraction is basically the change in direction of a light ray passing through another medium. So if we have a light ray in one medium and it suddenly enters another medium, then there is a shift in direction. This is due to the fact that light does not travel equally in all media. In some media, it's faster, while in other media, it's extremely slow. It's slower. So that is why there is a change in direction, which we call as refraction. Again, refraction has two laws. The first law states that the incident ray, the refracted ray, and the normal are all lying in the same plane. The second one is also known as Snell's law, and it states the sine of the angle of incidence divided by the sine of the angle of refraction is a constant. And this constant is referred to as the refractive index. Refractive index is basically a property by which it can bend light. So this is a relative quantity. It's mostly measured with respect to air to find absolute values. And if you have two separate media close to each other, then you find the refractive index with respect to both those media. So sin I by sin R is equal to mu2 1, that is refractive index of medium 2 with respect to medium 1. So mu2 divided by mu1 will be the value of sin I by sin R. And refractive index can be found out as the change in speed, the ratio of the speed of light in both these media. So mu2 by mu1 can also be written as v1 divided by v2. Now, in terms of the depth of the object, we can also write refractive index as the real depth divided by an apparent depth. So basically, suppose you're keeping a coin down here, then you're filling the bucket with water and you're viewing it from above. From above, what you'll see is that the coin is seen somewhere around here, whereas originally its position is at the bottom of the bucket. So what happens is that there's a raise, the image of the coin is getting raised up due to refraction. So because of this refraction, we find that the depth of the object that we see is not exactly its real depth. It's called the apparent depth. So using the difference between the real depth of an object and its apparent depth when viewed through a medium, you can find the refractive index as well. Now, when we're using a glass slab, such as this scenario, you find that the image, it enters from one medium, travels, refracts in the second medium, and then finally it goes out into the same medium. However, the first and the last rays have a shift in between them. This is called as the image shift or the lateral shift. And this lateral shift can be written as delta t is equal to 1 minus 1 by u times thickness. Now this shift can also be observed if we keep a refracting surface in between a light ray. So if suppose a light ray was traveling straight and forming an image, then if you keep a refracting surface in the middle, then you find that the image gets shifted by delta t. And that delta t is the value of image shift. It's using the formula 1 minus 1 by u times t. So that is the simple part about refraction. Now, let's take a special case of refraction. This has to do with critical angles and total internal reflection. So until now, we've been talking about light passing from a rarer medium to a denser medium optically. But what happens if light is traveling from an optically denser medium to an optically rarer medium? So as you can see, if it's a straight line, there is no refraction. Light goes straight. When it is oblique to the surface in between the two media, then what happens is that light bends away from the normal. And this occurs and occurs until there reaches an angle called IC, at which the angle of refraction becomes 90 degrees. This angle is referred to as the critical angle. It is the incident angle for which the angle of refraction is 90 degrees. In this scenario, we can write sine I divided by sine R, where R is 90, so that's sine 90, is equal to refractive index of the first medium, the second medium is 1, and refractive index of first medium is, say, mu. So sine 90 is also equal to 1, so sine I is now equal to 1 by mu. And we can write the angle I as sine inverse of 1 by mu. Now, over here, you see that they're using theta c in order to represent it. You can also represent it using the symbols IC or just C in order to represent the critical angle. So, in order for refraction to occur, the angle of incidence at the separation between the two media has to be less than the critical angle. At critical angle, the refracted ray grazes the surface of the water. So what happens if your angle of incidence is greater than the critical angle? You find that instead of refracting out towards the second medium, the light ray is getting reflected back inside. This phenomenon is known as total internal reflection. When a ray passes from optically denser to optically rarer medium, if the incident angle increased is greater than the critical angle, the entire light ray is then reflected back to the denser medium. This process is called as total internal reflection, and it has many purposes. One very good purpose that it is used for is in diamonds, where diamonds are cut in order to make them sparkle. That is due to total internal reflection. And another use is for optic fibers. So if you've seen those wires which you use for your local access networks, you find that instead of copper, you find a plasticky sort of thing that is running through the wire. Those are basically what we call optic fibers, and those are made of materials such as silica, which contain a high refractive index. So therefore, in one end, if we make light incident on it such that it gets totally reflected throughout the wire, then you can basically transmit information through light rays and you can get faster communication. And the advantage for this one is that there is no loss of energy. TIR has no loss of energy. Whereas if you are looking at normal reflection, then when light strikes a surface, there is some loss of energy, but in TIR, there is no such loss of energy. That's why optic fibers use TIR in order to communicate, in order to enable communication between various parts of the world. So that is about total internal reflection. Now, these parts, refraction of light, image shift, total internal reflection, etc., they were occurring when the surface of the surface between the two media was straight. It was a straight line. What happens when that surface is spherical? The refraction becomes spherical. What we consider is that this small part of the refracting surface, which is spherical, we consider the small infinitesimal part as a plane surface, and we apply the rules that we used for normal refraction. You add a normal which is perpendicular here, and then you refract the light ray with respect to that normal to get a short image. And you have object distances u, image distance v, etc. And you have the two refractive indices n1 and n2, which we can also write as mu1 and mu2. So if from an object we were to cast a light ray which strikes this spherical surface, it gets refracted by an angle r, and then it forms an image at the principal axis, say at a point I. So we can now, using various equations, we can relate the object distance, the image distance, and the radius of this refracting surface. So mu2 by v minus mu1 by u is equal to mu2 minus mu1 divided by r, where mu2 and mu1 are the refractive indices of medium 2 and medium 1 respectively. V is the image distance, u is the object distance, and r is the radius of curvature. Radius of curvature. For magnification, it's always height of the image divided by height of the object. Over here, we can write the height of the image as mu1 times v and height of the object as mu2 times u. So that can be further written down as r minus v divided by r minus u if you want to just explain magnification in terms of the distance and not in terms of height. So this is a classic case of refraction on a spherical surface. Now, why is this part important? Because this is the part that helps us to find out the object distance and image distance, as well as the focal length of a spherical lens. Now, lenses that we use today are also spherical, and we usually use biconvex and biconcave lenses. Biconvex, both sides are convex. Biconcave, both sides are concave. So basically, when this happens, you're basically having two types of refraction at the same time. When the light ray hits this surface, let me see if I can magnify that portion. Here we go. So as the light ray goes up here, then it becomes, so as you can see, it hits the first refracting surface. So then we can find, using the refraction due to spherical surface, we can find its image. However, there is also one more spherical surface. So that means there is more refraction occurring. So that refracts the light ray even further towards the final image distance, that is I. So when we are using derivation, we arrive at the formula 1 by V minus 1 by U equals mu2 minus mu1 divided by mu1 times 1 by R1 minus 1 by R2, which we can write down as 1 by F. So let's divide mu1 and separate it to both ends. So mu2 by mu1 on one end, that becomes mu2 with respect to 1. And then the other one becomes minus 1. And the other bracket has 1 by R1 minus 1 by R2. So if you can see, both these formulas have the same right-hand side. The right-hand side remains the same. The left-hand side, however, can be equated together to get the lens formula. 1 by F is equal to 1 by V minus 1 by U. Now, this second formula is what we call the lens maker's formula. So a lens maker, he uses this formula in order to make a lens of a suitable focal length. He will know the refractive index of the material and the radius of curvature for both the surfaces of a convex or concave lens. So that is how he makes a lens using for a suitable focal length. He uses the lens maker's formula. For our calculations, we'll be using the lens formula in order to find the object distance and the image distance. And again, in this case, lateral magnification is height of the image by height of the object, which is just V by U. Positive V by U is for lenses, negative V by U is for mirror. And when it comes to the formula, it's the exact opposite. 1 by V plus 1 by U is for the mirror, while 1 by V minus 1 by U is for the lens. So this is how you calculate the object, the image, and the focal length of a convex or concave lens. Again, in grade 10, we've studied the different cases by which an image forms in a convex and concave, in both convex and concave lenses. So I urge you to watch that video again as well. Now, moving on to the power of a lens. Power is basically referred to numerically as the reciprocal of focal length, F. But if you're trying to define power, then we would write it as the amount of convergence or divergence achieved by a lens. So the amount of convergence or divergence achieved by a lens is referred to as the power of that lens. Now, numerically, we represent it as the reciprocal of focal length. So P is equal to 1 by F. This is for a single mirror. Suppose if we have two lenses. So this is a convex and this is a concave. We know their focal lengths, say F1 and F2. Then for a combination of lenses, if you want to find the power, we use P is equal to P1 plus P2, power of the first lens plus power of the second lens. Power of the first is 1 by F1 and power of the second is 1 by F2. So P is equal to 1 by F1 plus 1 by F2. If there are more than two, then we just add the reciprocals up. Now, the reason why we're studying power for a combination of lenses is because this is more applicable for real life. Most of us, if we want to have to correct our eyesight, then we most probably use combination of lenses in order to find the correct focal length of the lens for which our eyes are suited to. And that's why we find out power for a combination of lenses as well as for one single lens. And don't forget, the SI unit is in diopters, or D. Now that we've studied the power of a lens and the lens formula, along with the magnification of images, let's look at another aspect of refraction: refraction through a prism. A prism is basically an instrument which contains two refracting surfaces, which in this case is AB and AC, and a base which supports the two surfaces. So that is the basic structure of a prism. Now in a prism, you can see that light here gets incident on one of its surfaces. This is the normal here. So light now gets refracted along this direction until it reaches the interface between the second and the first medium. So now it moves away from the normal. So the light is now reaching the first medium. In this prism, there are a couple of angles which we need to take care of. So the angle of incidence, the incident ray is in this direction, but if you notice, the emergent ray is in a completely different direction. The angular displacement between these two rays is what we call the angle of deviation. And for a prism, the angle between the refracting surfaces is called the angle of prism, or angle A. According to the formula, the angle of deviation can be written down as angle of incidence plus angle of emergence, which here is represented as I dash. You can represent it using the letter E as well, minus the angle of prism. Now, this is for a normal case of deviation. What happens if we have a particular scenario where the angle of incidence is equal to the angle of deviation? Well, in that case, we get the angle of minimum deviation. So in the angle of minimum deviation, since I is equal to E, you get delta minimum as 2I minus A, which we can write it down as mu minus 1 times A if the angle of prism is very small. That means if you have a thin prism, then you can write the angle of minimum deviation as the refractive index minus 1 times A. That completes the prism. So how do we find the angle of deviation and the angle of prism in a triangular prism? So that's the topic for this year. Next, we'll be looking at scattering of light. So when light gets scattered, it basically gets redirected into different paths when interacting with particles. So if you've seen light from the sun, you know that it's white light, which contains a combination of 7 colors. So when it hits the atmosphere is made up of a variety of particles: dust particles, water particles, oxygen, nitrogen, hydrogen, etc., etc. So what happens is that each of these particles interact with the light. Because these particles are small, so they're comparable with the light. So now light starts to get redirected into different paths, and the scattering that occurs will be dependent on the wavelength. So longer wavelengths are scattered less, while shorter wavelengths are scattered more. Now, that's why you observe both of these phenomena. You see blue skies because blue gets scattered more. However, during the sunset, you see red because it gets scattered the least. And since the sun is a long way away, the least scattered amount of light enters our eyes. So that's why you can see red sunrises and red sunsets. Now, we've studied about optics, especially ray optics, but what about the instruments that make these work? Now, we've talked about a couple of instruments such as lenses, the human eye, etc., but there are some other instruments which are also really helpful in visualizing the world around us. So today in this chapter, the additional topic that we'll be dealing with is what are called optical instruments. These optical instruments are basically effective instruments that use the principles of reflection and refraction that are found in prisms, mirrors, and lenses. So these are basically a combination of prisms or mirrors or lenses. The first kind of optical instrument is what we call a microscope. So in optical instruments, we'll be studying two types of optical instruments, microscope and telescope. Microscopes, we can classify them as simple and compound. In a simple microscope, it's just a single lens which is giving you a virtual object, a virtual image, which is larger than that of the object. So if you can see here, you get a virtual image, and these light rays are further refracted inside the human eye in order to view this enlarged image of that object. So microscope is basically used to magnify small objects in order for them to be visible. So if you want to form this image at the near point, such as in this diagram, we use the formula 1 minus d by f. Over here, capital D refers to the distance, or more clearly, the least distance of distinct vision, basically the near point. So magnification at the near point is 1 plus d by f, while magnification at infinity is d by f. This is for a simple microscope that uses one lens. However, there are various challenges. For instance, say there's always the problem of spherical aberrations and spherical inaccuracies. So just one lens sometimes is not enough to magnify very, very small objects. So we use two lenses. One of them is an objective lens, which magnifies the image a little bit to get a magnified real image. And then the same magnified real image is now magnified even more by the eyepiece, which forms a very large virtual image of the small object. So a microscope with two lenses is what we call a compound microscope. So since we have two lenses, we'll have two focal lengths. One is the focal length of the objective lens, and the other is the focal length of the eyepiece. So when we're looking at magnification, the magnification here results from both the objective and the eyepiece. So magnification for infinity, it will be V by U times D by FE. FE stands for focal length of the eyepiece, V stands for the image distance, U stands for the object distance from the objective, and D stands for the least distance of distinct vision, which in normal cases is 25 centimeters. Now, if we have to find out the magnification for an image at near point, then we have to use a different formula, which is V by U times 1 plus FD by FE, which we can write down as minus 1 by FO times 1 plus D by FE. FE is the focal length of the eyepiece, FO is the focal length of the objective lens. So that is how you can magnify small objects which are near to you. You magnify them using a microscope in order to see their various parts. But what happens if the object you want to see is first so far away, and secondly, you can't see it because it's so small compared to you? That is when you use a telescope. A telescope is basically an instrument used to view enlarged images of astronomical objects which are far, far away. Telescopes can be classified into astronomical, the older kind of telescope which uses lenses, and the newer kind is known as Cassegrain telescopes, which use concave mirrors. So In an astronomical telescope, you use two lenses, again an objective and an eyepiece. The objective this time is larger than the eyepiece, so therefore the vast amount of light is getting concentrated into a small part. The small image is now used by the eyepiece in order to form an image of its own, which is magnified. So therefore, both these lenses work together in order to form a large image of a faraway object. Now, in order to form this image at the near point, we use the formula m is equal to FO by FE times 1 plus FE by D, where FO stands for the focal length of the objective lens, FE stands for the focal length of the eyepiece, D stands for the least distance of distinct vision. Now, if this image is to be formed at infinity, then the magnification of that image will be minus FO by FE. So therefore, magnification will then be equal to minus FO divided by FE. This is for an astronomical telescope. However, again, the problem here is that astronomical telescopes, they use lenses, and lenses usually form spherical inaccuracies. So what we have found out is that using concave mirrors, we can also find out, and you can also expand images. So light rays are now reflected by a concave mirror onto a secondary mirror, which reflects it again in order to give you a virtual, erect, upright, and also enlarged image. So through this eyepiece, you can see the object as clearly as you can see it through an astronomical telescope. And since we're not dealing with large lenses, these telescopes, the Cassegrain telescopes, are easier to carry and are more portable and durable. So that's how we have changed from refraction to reflection in order to view astronomical objects far, far away. So this is basically the chapter Ray Optics and Optical Instruments. We have a lot of formulae here with respect to reflection, the sign convention, which is applicable for all kinds of reflections and refractions, refraction of light, total internal reflection, critical angle, refraction on a spherical surface, formulae with respect to the lens, such as the lens maker's formula and the lens formula, then power of a lens, microscope magnification, and telescope magnifications. Also, we have formulae with respect to the angle of deviation in a prism. So this is an overview of the chapter Ray Optics and Optical Instruments. So we hope you found this interesting. For more useful videos, don't forget to subscribe to our channel, Brain Blitz Audios. We have a lot of educational content, and you can always be a part of that by clicking on our playlist and enjoying more of our videos. So until the next webisode, take care, stay safe, bye-bye for now.